Okay, so we just said that the search over the positive semi-definite matrices is something you can do with convex optimization. That's cool. That's maybe initially surprising already. It turns out that we're going to be able to search over positive polynomials using the same tools. Okay, so if I have a polynomial function and I want to ask, is it positive everywhere? Is it always greater than or equal to 0 for all x? Shockingly, surprisingly, that's also something that we can do pretty darn well with semi-definite optimization. All right, so we're going to search over positive polynomials. And really, it's very surprising that there's this strong analogy between if I write some polynomial, which say parameterized by alpha, over some variables x, okay, which in the univariate, if x is a scalar, then it's just polynomials, the ones you know about here, right? And of course, if x is a vector, I can still write something out. I could write it as alpha 0, alpha 1, x1, alpha 2, x1, x2, and some. That's not equality from there. That's just another example. Or I could write some polynomial in multiple variables, of course, too. And the claim is, if I want to, for instance, minimize over the coefficients, alpha, some convex objective, and the solvers consume linear objectives. If I want to minimize some, some objective, let's say C transpose alpha. Can't believe I wrote down alpha transpose x. Subject to the idea that for all x, P of alpha x is greater than or equal to 0. That's going to turn out, this is just my weights. My objective. Okay, this turns out to be something I could do with semi-definite programming. Or really a layer that sits on top of semi-definite programming. We call it sums of squares optimization. There's a few superstars in the world of sums of squares optimization. One of them is on the faculty here, Pablo Carrillo, is upstairs. He basically found this connection between sums of squares polynomials and SDP and systems theory for his PhD thesis. So if you guys haven't finished your PhD thesis yet, there's the bar right there. Yeah, pretty impressive thesis. So we reference the thesis as one of your background reading if you like. Okay, so, and there's actually, the theory of this is beautiful. There's lots and lots of connections. It's not a superficial connection. There's lots of deep connections between what people know about polynomials, which lives in algebraic geometry, and what people know about optimization. Lots and lots of really nice connections. And there's a class, Pablo teaches a class on it too. Okay, so in fact, I can put down lots of potentially, multiple polynomial constraints. Right, so this is a big idea. We're going to use it now to try to think about, first let me convince you that it's true, and then we'll use it to try to do Lyapunov analysis for nonlinear systems. Yeah? Or do you believe it's true? I think I have to say a little bit more to convince you, but let me try to say it efficiently. And just so you have the intuition, okay? So, all right, so how do I prove, if I have a polynomial like this, how do I prove that it's positive for all x? Right? So, well, the title sort of gives it away, but I mean, so let's just think about it. So, is this positive for all real x? Yeah, that's positive, because that's positive, and that can only be positive, right? All right, I got a better example here. So what about 2 minus 4x plus 5x squared? Is that one positive for all x? That's not as clear.
You can write it as a sum of squares.
If I can write it as a sum of squares, right? So turns out I can. Turns out if I write it like that, then a little bit of algebra will show you those are the same. And now you believe that it's positive everywhere. Okay. So how do I factor this into that, if that's the goal? It turns out, I think really shockingly, that I can ask an STP solver to factor that for me. Okay? So here's the idea. So I'm gonna slide transition here about a real estate. Okay? How do I ask an STP solver to factor something like that? Okay? You think about like symbolic things, trying a bunch of different factorizations. It turns out if I were to write it like this. Okay, so I'm gonna say I want this to be some combination of basic building block monomials, very simple polynomials, if you will. Let's say I'll write down, I've got to have some combination of these. I'll make squared combinations of these. Okay, and then I'm going to put a matrix in between. Oops. 3, 1, 2, 2. And these would be, I'll constrain it to be symmetric. Two. Okay? So I'm going to say, find me a matrix A, which, guess what, is PSD. I'll call that matrix A. And I'm going to ask it to be positive semi-definite. And if I can find a positive semi-definite matrix A, which also makes this equation true, then I've actually found my factorization. And it has to be a positive sum of squares by virtue of this being A. Okay? So I have this, I have some free parameters here I'm trying to decide over. I have a constraint that the matrix that they form is positive semi-definite. And then I have some extra constraints which have to be true for this equality to hold, right? So I know that A11, when I put it through, had better equal 1. That's the only thing that can equal 1. And A21, it turns out, had better be equal to 0. And A22 plus 2, I'll just cheat now, 3,1 equals 2. There's just just to make that equality hold, there's some constraints on those elements. But they're all linear constraints. They're my half-plane constraints. Or these are actually equality constraints. So they're line constraints. All right? And I can now put this together and say, find some A that satisfies all these constraints and is positive definite. And if I can find that A, then I found my factorization of that polynomial. That's awesome. That connects this sort of very symbolic feeling factorization problem into a numerical problem. It happens to be a numerical problem I can just call the solver and get an answer to. Okay? There's some caveats, some asterisks, some important side notes. It's there's a lot known about the gap between positive polynomials and polynomials that have a sums of squares decomposition. There are actually positive polynomials that for all x are always greater than 0, which cannot be factored into a sum of squares. So that's a bummer, but that's okay. It turns out for us that's not going to slow us down, because I mean the basic idea is that there's so many Lyapunov functions that can prove stability of the same system that the fact that maybe I'm going to search over not every Lyapunov function, it's going to be okay. All right, but I have to sort of say that there's cases where it's known to be tight, but there is potentially a gap between the positive polynomials and the sums of squares polynomials. Okay, so that's the intuition of how you'd use an STP to factorize a matrix, and really the trick is listing these monomials out and then doing some linear combination, some combination of those monomials. So like the complexity is maybe in listing out the monomials. There's a lot known about what monomials you need based on the total order of this. So you don't have to guess them. The solvers will do that for you. Okay, but you could maybe think about this like, I don't know, if you're a machine learning person, think of it a little bit like the kernel trick, right? Or it's a little bit like our function approximator. The fact that we can do great things with linear function approximators, even though they've got nonlinear basis functions. In some sense, the richness is in the basis functions, and then simple combinations of them can do great things.